So welcome everyone to today's webinar. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. In today's webinar, we're looking at thermal conductivity testing 101, really kind of going over some of the theory and applications. We're trying to cover off a few different method types, where they come up, talk about transient, of course, as being a core focus, but also reference some of the other methods, such as like steady state, and really just kind of go over where they come up, where they're best applicable for, and also what are the requirements and considerations in using some of these different methods. So again, this will be very high level, covering kind of a broad range of approaches here, all centered around thermal conductivity. So to kind of start things off, just a quick introduction to C-Therm, who we are and what we do. So C-Therm Technologies, we focus on thermal conductivity. This is really our purpose, specifically developing transient methods. So a bulk of today's content will be on the transient class of thermal conductivity methods. And again, we'll go into that in further detail. And really the whole idea and the purpose of what we really try to advocate for is simplifying thermal conductivity testing for the materials of tomorrow. And as we know, materials are getting more advanced and complex, but we need good thermal conductivity data to obviously support those development efforts. So to introduce our Trident platform, so this is C-Therm's core instrument. You can see here, Trident was developed as a modular system, brings together 4 different methods for thermal conductivity. And again, we'll go into each one of these here today. But the whole idea with a multi-method approach is that there will be scenarios where certainly maybe more than one method is appropriate for a given sample or test condition, but there will be others where really selecting one that is really designed for the task at hand can be quite important. So again, with Trident, you have this multi-method avenue that you can pursue, so you're not locked into one singular approach and trying to make everything fit. And the whole idea behind Trident, really, this quote here from Abraham Maslow, we like to reference: when all you have is a hammer, everything looks like a nail. So again, the idea, if you just had one tool for the task at hand, so one method for thermal conductivity, sometimes you can get stuck in really trying to use something that just really inherently wasn't designed for what you are looking to measure. And again, we'll kind of talk about those different scenarios as we go through the content here today. I will mention this resource here, our method selection guide, thermal conductivity. This is available as a free resource download. This will cover off a lot of what we're talking about here today, but also go into a little bit more detail on some of the other methods, some of the steady state techniques, and even some of the other more novel approaches that exist out there. This was recently updated just towards the end of last year, so this has got a lot of really good content in it. Again, for folks that may be new to the space, or if you've been dealing with thermal conductivity, but maybe want to learn more about what options exist out there, this is a great resource to take a look at. So jumping into the content here, what is thermal conductivity? In terms of its use case and where it plays, it is across a variety of different applications and industries, but it all centers around, thermal management, heat dissipation, and how do we quantify this? So thermal conductivity is really describing a material's ability to conduct or transfer heat. All of the data that we'll be talking about here, when we kind of show examples, it'll be in units of watts per meter Kelvin. And as we're going to go through, we're going to see certain areas where, of course, increased or higher thermal conductivity is beneficial. But also on the low end, there are certain, insulation examples that can come up as well. So a low or a high thermal conductivity isn't necessarily good or bad. It is very contextual, of course, to the application and the materials that you're dealing with. And, as an example of this, very simple one, but cookware, or something that we are, looking to have heat transfer through efficiently, such as this cast iron, you want a higher thermal conductivity versus, to reduce the potential burning or, protection, a lower thermal conductivity, more insulative material like this towel is going to be there to accommodate that. So again, depending on what we're looking at, this would really dictate what your end goal should be in terms of, a specific performance output. Um, and, related to this, certain materials with high thermal conductivities and low thermal conductivities, different methods are oftentimes best suited for some of those considerations just in of that of itself. And then, of course, we can start looking at all the other aspects like, temperature and testing conditions on top of that. So we kind of mentioned thermal conductivity. This will be, by and large, the core focus of what we're going to look at here today. But there are other material properties, other thermal properties of interest for some folks. Another popular one is thermal diffusivity, and then also thermal effusivity. So you can kind of see these kind of three different properties and how they're related. Most often through of course, the density and the heat capacity of the materials. But again, depending on this industry or the application, there can be sometimes more relevance towards one or the other. Generically, here today, we're going to be talking mostly about thermal conductivity. So this brings us to the kind of an initial point on the method. So how do we actually test this? As I said, we focus primarily on transient here at C-Therm, but the other large category of measurement techniques is steady state. So steady state, you have your things like your, guarded hot plates, heat flow meters, things of that sort. So we'll kind of do a little bit of comparing and contrasting between some of these approaches. Excuse me. All right. So starting out with steady state, heat flow meters, guarded hot plates, just kind of a generic example setup here of what these systems typically look like. So steady state, you'll generally have a dual plate style design. One's a hot side, one's a cold side, and your sample is placed in between. Often you'll see, ASTM C518, C177 very commonly referenced, especially in insulation industries. And, this makes sense, of course, because really these steady state techniques very good at testing the lower K materials, the more insulative samples. Some other things that we'll talk about in terms of all the methods here, but with heat flow meters and these steady state approaches, a nice benefit is they do measure through the entire thickness of your material. Again, because we have that kind of dual-sided design, the measurement is going through the entire piece. And because of that, they are quite attuned at testing multi-layered samples. You've got to see here some, if you're familiar with insulation, then this isn't anything surprising, but, different types of, construction materials like rock wool, maybe it's an expanded foam, whatever that may be. Very common test, like this was a technical data sheet kind of referencing C518. Now I will just maybe clarify, oftentimes when we talk about C518 or steady state, everything is in terms of R value or thermal resistance. So thermal resistance this is related to thermal conductivity, but it takes into account the overall thickness of your material. But all that is to say, if you ever encounter an R value or thermal resistance value, and you're wondering how do I get, or how does that relate to conductivity, it's basically thickness divided by the material's thermal conductivity. Now, with steady state, there are some considerations to be mindful of. Generally speaking, they are much longer in terms of test times. Hours to even days in some instances isn't uncommon. Part of why that is fundamental to how the measurement is performed. This is a little excerpt from ASTM C518, kind of talks about, your time and measurement intervals. But with steady state, there's a really important requirement that everything is, as it gets its name from, in a steady state condition or very stable. So there's essentially no temperature change as a function of time. And with that, to really conform strictly to the standard, you can see every 10 minutes, intervals of at least 10 minutes, you have to make successive observations where you have very, very small deviations occurring. So generally, and again, this can vary depending on the overall conductivity and how thick the material is, but at the test time is a key factor to consider. The sample geometry or the sample size requirements is another thing. Generally, the steady state devices, you're dealing with larger size, call them like blocks or pieces of material, 30 centimeters by 30 centimeters is a very standard size for many instruments out there. And again, while that may work very well for some of the mass-produced materials, this was a kind of an image of I believe it was actually a bio-based insulation from a group in 2024, and you can see the size here. These are very small pieces. One of the challenges that come up a lot in R&D, especially, is, well, can we actually even produce the sample to the size requirements of some of these methods? So another kind of angle to think about in terms of which method is going to fit for your testing. As I mentioned, really good for low K. I'd say industry standard for a lot of insulation activities, but not so great with the higher conductivity materials. There are certain steady state systems that push those limits a bit, but generally geared more on the low K side of things. And the last part here that I like to really mention, and this will be true for some other methods as well, but specifically to the heat flow meters, because they average out or measure out over the entire piece through the full thickness, it gives you this nice fully averaged out value for the entire material. But in some contexts, you're maybe wondering about your material's consistency and, how can we verify this? And with something of this type, it's not inherently possible. So you're kind of measuring everything together. And we'll talk about some use cases where maybe those types of consistency checks could be really important and how we would go about doing that. So that was just, kind of quick info on some steady state, but we're going to go into a variety of the different transient methods that we offer here, looking at all four, starting with our MTPS, TPS, TLS, and then finishing up with THW. Won't go over every little detail on the slide, but the whole, I'd say, maybe thing to take away here is each method, of course, has different ranges of performance, different temperatures that they can accommodate, different standards that they conform to. That's sometimes a really important aspect to consider is there a kind of an industry standard that you need to have in your toolkit? Or maybe, is this early R&D development where, you're just looking to get the quickest, easiest way to get some data for you. So we'll talk about some of these considerations. Now, overall, this is, again, kind of generalizing all of these different transient methods, but they do have some fundamental underlying similarities in that how these measurements work on transient, unlike steady state, which again has like that dual-sided plate design, transient, you're going to have your sensor. Sometimes, it could just be a single surface point of contact. Some of the methods are double-sided, etc. But the sensor is placed in direct contact with your sample of interest. And these sensors are electrically heated to provide some thermal input to our system, which is, of course, going to change as a function of time. So you'll see a temperature rise occurring, and we are monitoring that change. And the whole idea with how this data is being analyzed is that we are not waiting for this, again, steady state constant point to be reached. We're actually doing the analysis in the earlier region by essentially looking at the change in slope that occurs over the transient zone. So part of this really comes to the fact that transient will always be inherently a faster measurement compared to some of the more traditional approaches. On average, we're looking seconds to minutes in terms of your overall test times. Again, compared to like hours or days with steady state. So oftentimes in R&D environments, especially, transient really has some nice benefits just from the speed of measurement alone. Now, there are some additional considerations to keep in mind, and this will vary or be slightly different depending on the method, transient, steady state, or otherwise. And it's important to kind of keep these in mind. The depth of analysis. So how far are we actually, let's say, probing into the material? Again, when I was saying like steady state measures through the full thickness, transient does not necessarily do that. Again, depending on your specific method, there's actually an assumption of a semi-infinite medium for most kind of standard transient tests, where you're assuming that the heat pulse is actually contained within the body. So we're actually never penetrating through the full thickness. And then how does that translate to the outputted results? Um, in a similar vein, the directionality. So is your material isotropic or is it anisotropic? And if it is one or the other, what is my sensor actually measuring? There are some methods that are directionally dependent. Others will kind of average out over a kind of a larger area. And again, understanding those implications on the material based on the directionality can be quite important. Thermal stability. So I mentioned this in terms of, as you're taking measurements, depending on how much total thermal input you're generating into our system, this can have a bearing on kind of your cool down time between individual measurements. Especially with transient, it's very important that your sensor and your sample, before you initiate that test, that it has come to a stabilized condition, or else you can get some potential bias introduced based on that, let's say, instability in your overall setup. And then the environment that we're testing in. So whether that's, different temperatures under different compressive loads, inert gas environments, humidity, etc. Again, these can all play a role in the influence on your effective thermal conductivity. And if those variables are relevant to the application, they can, of course, be very important to quantify. Getting representative testing conditions is really one of the big things that we advocate for. Is if in application, let's say your compressible foam is going to be densified under an applied load, maybe potentially exposed to partial saturation or kind of a high humidity environment, well, you would likely really want to test that material under those similar conditions to be able to get some good comparable and representative data. So again, we'll kind of talk about a few of these examples as we go forward. So the first method here, the MTPS. So this is the modified transient plane source. Kind of see what the sensor looks like. Active area where the measurement is taken, it's about 18 millimeters in diameter. So we need to make sure we can cover that surface with your material of interest. With the MTPS, this is a patented method from us at C-Therm, and one of the reasons for that is related to the gartering, and this is a component that goes around the active area of the sensor. And what it effectively does is help promote a one-dimensional heat transfer into your sample. So when we're kind of talking earlier about measurement directionality, this is one that is really good for assessing localized kind of spot measurements on a material, because wherever you're placing that sensor, you can view that kind of direct spot as what is being assessed. We're not kind of measuring outwards. We're going at that location up into the material. Now, in terms of the different, let's say, sample thickness requirements for MTPS, this varies depending on the thermal conductivity range, kind of the material type that we're working with. Generally, we're in the millimeter size range, unless you get into some very high conductivity materials. Again, there's inherently no maximum size limitation here. But again, keeping in mind that probing depth, or how far we're actually penetrating into the sample, that's going to be, I would say, what is a key factor to keep in mind, because you could have a sample that's 10 centimeters thick, but we're only going to be probing maybe a few millimeters into that, again, depending on the sample that's in question. With the MTPS, it's also a really nice option because it gives you testing capabilities for not only solids, but also non-solids as well. So liquids, powders, and pastes. There's a little metal attachment here called the liquids and powder cell. You basically just pop it on. Gives you a nice way to kind of give you a good coverage on a variety of different materials that you might be coming up against in your testing scenarios. Now, I want to give a few examples of where the MTPS is commonly employed, and of course, a big area of application as, everything from, electric vehicles to, wearable technologies, whatever it may be, thermal interface materials are highly, highly relevant. And these can take different sample or different formats, but the big thing is that they are here to improve heat transfer between components. So typically you're targeting higher thermal conductivities as being kind of preferred. This is generally when you look at like a thermal interface material, like technical data sheet, like thermal conductivity will be specified as one of those key performance metrics. Um, but really, I want to talk about TIMs in terms of the fillers, because fillers or these additives are what are really tailoring that specific performance. If you take a base silicone material, it's quite low in thermal conductivity. So when we look at all these thermal interface materials that might be, 1 or 2 or 5 watts per meter Kelvin, how people are achieving this is through the addition of additives or these conductive fillers within the system. But what or how do we know if my material, that additive, is consistent within the sample and uniform in its dispersion? Because that can be really important here. Um, so we have essentially a use case called thermal mapping, because if your material is not uniformly dispersed, that filler isn't distributed uniformly, this can cause us some issues. If you're getting things like agglomeration or sedimentation of that filler, from a material perspective, and again, especially in a thermal management system, you're going to get potentially uneven heat dissipation that can result in performance decreases, but also safety risks in a worst case scenario. So from a material side, it is something that many groups are looking to verify and, of course, ensure that it's not happening within their products. But then from a testing perspective, because of that non-uniformity, this is something that can potentially introduce bias and into different degrees depending on which method is being used. And with the MTPS, because it's a single-sided method, and again, that controlled directionality that it has, we can do what's called thermal mapping. So you might have a sample like this, and as we can see, very non-uniform in its dispersion. But by placing the sensor at these discrete locations across the material, we can actually very quickly map out those localized values at each spot and use that to develop an understanding of the overall consistency within the material, or in this case, the lack thereof. So as a means of I'd say very quick testing, MTPS can kind of come in and do these kind of individual locations, pick up on some of those potential issues early on in that development cycle to ensure that you're able to iterate and get that product to market in an optimized manner, in a faster way. So MTPS, especially in the R&D development side, has quite a lot of unique advantages because of the sensor design, the single-sided nature, etc. Now, kind of talked about insulation and kind of how steady state is really good for it. But we're seeing a lot of, both in kind of industry now, but also in academia, quite a bit bio-based materials. So these are samples, of course, that are produced from renewable sources. These could be everything from, cellulose, hemp, wood, flax. There's a variety of different options out there. But these bio-based materials in and of themselves are typically less consistent than their synthetic counterparts, just by nature being kind of naturally occurring. So these are some things that can also introduce, like, how do we verify, the consistency, and is that even relevant in this application? The other aspect is, in some cases, like the example I showed, it could be difficult to produce maybe the larger sample formats needed. So again, shifting to a steady or a transient method with smaller sample requirements can often be sometimes a nice benefit or even a requirement to be able to get some good quality data collected. This paper here, it's really one I really like. It's from quite a few years back now, but it was a group looking at bio-based insulations using bamboo fibers and bioglues. And I just want to highlight here, when they were actually referencing the thermal conductivity data on their MTPS, they were doing it based on thermal conductivity as a function of density, but even you can kind of see even the same sample, different specimens of the same lot, there was some inherent variation. So kind of quantifying that shift. Now, is that a significant shift or not? But as you can see, they kind of clustered them into these 3 different kind of groupings. So overall, kind of understanding, maybe testing, again, either at different locations on a sample or testing a sample multiple times can give you some really important insight. The other nice thing with these transient methods is, again, the environments that you can place them. This group was very interested in testing the materials under different relative humidity conditions and seeing how that impacted performance. And they actually did quite a long study. It was like a month-long study by cycling from a low to a high humidity state and seeing that relative change in thermal conductivity. Interesting with bio-based materials, they are typically more attuned to being able to handle those shifts based on humidity changes. Whereas if you're familiar with more traditional synthetic insulations, typically once they get wet or kind of saturated, very sharp drop off in performance. So you kind of get an increased thermal conductivity or view that as a decreased thermal resistance. And then lastly, for the MTPS, I'd be remiss if I didn't talk about the ASTM D7984 standard. So MTPS has a standard for the thermal effusivity measurement of textiles and fabrics. This is, I would say, one of the very common uses for soft goods like apparel, bedding, anytime where we're concerned with the perceived touch or feel of a material. This effusivity is often used as a metric for quantifying that comfort. So the ASTM kind of dictates different considerations on the setup requirements, environmental conditions, etc. But what it allows for is a framework for consistent testing and comparability across different fabrics, textiles, and things of the sort. But what is effusivity? Again, I kind of mentioned it earlier on at the beginning, but you may see it referred to as thermal inertia, but really how we define it is its ability, it's the material's ability to exchange heat with another body that it's in contact with. And, the case example when we're talking about perceived feel is, let's say the hand or the body, touching, a fabric or the clothing that you're wearing. How does this kind of comfort level come through based on the warm feel or cool touch of the product? Again, this is related through thermal conductivity. You kind of see how those calculations can be run. But again, effusivity really gives a nice overall structure for quantifying perceived feel. And we kind of have, you can see this is a very generic kind of example, but generally lower effusivity, the lower that value is, the more warmer feeling the material will be. So these would be, things like your fleeces and your wools, as compared to more cool feeling fabrics, such as, cottons, sportswear materials, etc. So where effusivity is coming up, we see it a lot in, claims validation. If you're looking to quantify something based on, a cool touch property, effusivity is often used to benchmark those types of performance considerations. It's also very highly applied in different consumer marketing. Again, like effusivity, kind of showing, the cool aspect of different products. So whether it's for like internal material validation or kind of external marketing claims, effusivity is certainly a strong candidate for material metric performance. So switching to the TPS here. So TPS is, as you can see, very different in its design compared to the MTPS. It's similarly has kind of a circular spiral heating element on the end. This is where you kind of have your sample in contact with. But past that, it's quite different. It's very thin, it's flexible, it's actually double-sided, so you'll have some considerations around your test setup and sample requirements here. And as you can see, it comes in a few different sizes as well. Now, when we talk about TPS, the TPS is very, I would say, separated in terms of its functionality. So we have different utilities or modes of operation to accommodate different sample types. And the bulk utility, this is like your entry form of TPS testing, really geared towards larger size bulk materials. Excuse me. And the thing I always just like to mention with the TPS is that your sample requirements are not based on anything related to the material type or the conductivity range. Rather, it's based on the size of the sensor that you use. So as you can see, there's a 6, 13, and 30 millimeter size sensor by default. Your diameter and thickness scale based on the size of the sensor. Now, as we kind of go through, I would say 13 millimeters is the standard size. If you have a sample that just simply can't be produced in like a big enough format, you can go to the smaller sample. The 30 millimeters is actually the largest, and you can say, well, what's the benefit of using that? Well, if you're testing something potentially more, let's say there's more heterogeneity involved and we're trying to capture a larger assessed area, again, kind of talking about differences in measurement depth of analysis, having a larger size sensor may capture that kind of deeper kind of overall volume and give you a more representative output. So again, certain considerations on that side, but for the bulk utility, again, whether you're testing, common examples would be like things like concretes and cements, certain geological samples, also like polymers, insulation as well, but there are unique to the TPS some of those materials that are potentially hygroscopic or would react or absorb with water. Some of our methods require contact agents, while the TPS does not. So it has some nice capabilities there. This was some example on some geological samples that we tested, both under a kind of fully saturated and dry state. It was interesting. You could see that the sandstone sample, when we tested at under 100% kind of saturation, quite a bit higher than in the dried state versus the shale, which was, I'd say, almost insignificantly different between those two. So in this kind of context, again, the kind of the environmental or the, let's say, the conditions that we're subjecting the material to, saturated versus non-saturated, can give you differences in that effective thermal conductivity. So something that potentially could be interesting, especially in geological and geothermal applications, very common for us here. Certain unique capabilities on that front. Now, the TPS does carry a variety of unique additional options for testing. These do handle more, let's say, novel kind of sample formats, everything from thin films, anisotropic samples, slabs, which are generally kind of thinner, more conductive materials. So I want to kind of share a few different examples of that. So all of these kind of specialized utilities will operate using the same TPS sensor, but the setup could be a little bit different. For example, your slab setup will involve the use of the sensor in your two samples, but with an insulative backing material on either side. Some kind of, I'd say, common applications here, again, kind of thinner, more conductive materials. And the reason why slab is really great is because generally speaking, for like TPS bulk or like even the MTPS, you need quite a large piece to measure. Some of these, like let's say the aluminum sheets, typically provided quite thin. So this gives you a kind of just an easier path forward on testing those types of samples. This data was actually on some very thin, very conductive graphite sheets. So this was some data that we've tested, and you can kind of see the thermal conductivity is approaching just shy of like 2,000 watts per meter Kelvin. So thin conductive materials, really a good fit for TPS slab. Now there's the anisotropic utility, and this, as you can tell from the name, is for testing materials that exhibit different in versus through plane thermal properties. One thing just to flag for the anisotropic utility is that it does require that the material is radially symmetrical. So when we're talking about, through plane, this can obviously be different from your in-plane direction, but within that in-plane, there has to be that radial symmetry for this specific utility with TPS to be valid. The other thing is it does require the manual input of volumetric heat capacity, so CP and density, within the system in order to basically separate out the two terms, the in-plane and the through-plane contribution. But again, this can be really important because if you are dealing with a material that is significantly different in those two planes, heat spreader versus heat, like heat transfer, like through the body or spreading out over an area, excuse me, that can sometimes be really important to quantify. And if you were to treat a measurement like this, or treat a sample like this as a bulk material, what you're going to get is just kind of one average value of the two components. But if we need to kind of really quantify this different aspects separately, TPS anisotropic setup is a nice capability to take a look at. And then lastly, our thin films utility. So thin films here, we're talking down as low as about 10 microns in thickness, typically on the lower conductivity side, like more polymer-based films. And this is actually, I'd say, the most different in terms of how you set up a measurement and run a test. It actually involves this successive layering procedure. So it's not just done with kind of like the sensor and the sample in one single run. It's actually a 3-point measurement. So you'd start with a blank, And your blank measurement is actually your sensor, no sample at all, and a conductive backing material, um, followed by a measurement with your sensor and backing material, but with one layer of the film added in. And then you would repeat this one final time for the third measurement, which is the one that has a second doubling or extra layer of film within the system. And how the data actually kind of comes out is we're essentially building a thickness versus a change in temperature linear regression to be able to quantify the thermal conductivity of that material here. So you can kind of see it's this 3-point measurement that is produced for that type of analysis. So TPS, there's a lot of different kind of functionalities baked into it. So to quickly recap, your bulk option is this is for your basic, larger isotropic materials. The anisotropy utility is, of course, for obtaining a separation of the in and through plane thermal conductivity of a sample that exhibits radial symmetry. Slab is good for very thin, high conductivity samples and is more, it's representative of the in-plane direction, versus thin films, which is really good for the thinner, lower conductivity samples, representing in the through plane direction. And the last example I wanted to share here is, technical data sheets for, thermal interface materials. Again, we're kind of coming back to that TIM application. TPS, transient plane source, ISO 22007-2, or like hot disk style sensor. These are all words for the kind of the same method here. So you'll see on a lot of technical data sheets that this is referenced for the thermal conductivity value. So for this like thermal interface material we purchased, we tested it with our TPS. And as we can see, results lined up within the expected, accuracy range around that 2 watt per meter Kelvin mark. So this is an example of, good, well-optimized material, technical data sheets aligning with, like verification tests, always something that you like to see. But a question you might have is, well, let's say, we're talking about TIMs on MTPS and TIMs on TPS or even some other methods. So how do you kind of compare different methods, different approaches? So we took the same sample, measured it on MTPS. As you can see, there's a slight shift up here, but still within that plus minus of that 2 watt per meter Kelvin spec value. But I always like to clarify that getting good agreement between different methods on a sample is possible when the material is inherently consistent, well optimized, and uniform. Where you'll start to see larger deviation between different methods is when this is not true. So kind of coming back to an MTPS example where, we have a sample like this, testing at different locations, you can see gave different results. But if we took a sample like this, or maybe made a duplicate pair and kind of again non-consistent top and bottom, and we measured that, well, what do the results look like? And what they will actually kind of show here is a TPS value somewhere above the minimum value of MTPS, but below the maximum. And the question then becomes, well, which value is right? What is the true value of the material? And in that context, unfortunately, I would say both are right, but they're for different reasons. Again, each one of these MTPS results is local at that specific point that we're testing. TPS here is measuring and averaging out over a larger area. So again, kind of that whole idea of what is actually being measured, how deep are we going into the sample? Because if this was a perfectly uniform material, it would be the same number just kind of flat across. But when you get materials that are not well optimized and you're kind of comparing different methods, this is oftentimes where confusion can come up because method A versus B versus C can give different results. So ultimately, if you run into something like this is a really good example of where really going in and trying to understand, well, maybe my material isn't as consistent as I thought it was, and how can I confirm that? So again, that MTPS mapping is a really nice way of getting at some of those kind of understandings and kind of getting your materials optimized in an efficient manner. TLS. Okay, so now we're on to, I'd say, the third method here, which is quite different in design compared to the first two that we looked at. This is a needle probe style sensor, the transient line source or TLS. You'll see it applied in a few different areas, typically in, I'd say, for polymers, testing, and then also like geological, soil, soft rocks, and aggregates. There's two ASTMs that it conforms to in those two different sectors. Um, Now, if you're testing any non-solid, there is a standard cell that, typically is provided. You would fill that up. It holds about 60 milliliters. You insert the probe down into it and do your testing. Alternatively, technically, if you just had like a large vat or like a container of material, you could just stick the probe down into that. You can use the TLS for testing solid samples. The challenge, or I'd say the consideration would be you're gonna have to drill into it because you're gonna have basically a slot or a hole that the TLS needle can then fit into. So adds a little bit more sample prep considerations if you want to test solids, like bulk solids with TLS, but it is a possibility. Um, where we see it more commonly employed, so polymer melts being a really popular use case for the TLS, being able to test up to about 300 C with this TLS probe allows for some nice characterization of different polymer melts, whether that's being used for like 3D printing or injection molding applications. The TLS also has pressure capabilities. I have a slide towards the end that we'll talk about that a little bit, but it gives you the ability to test as a function of temperature and pressure, which again, in kind of some of these polymer melt applications can be quite relevant. Like I said, though, polymers is one area. The other one is more like geological, soil, soft rocks, etc. So this is some testing on some potting soil, actually. So you can kind of see some interesting things where, if you have a loose sample like this, well, the effective thermal conductivity is going to be representative of, how packed it is and the overall, like the conditions on top of that. So you can kind of see how this plays a role where we took the sample first, tested it under a loose state, had a value here, packed it a little bit, again, densified that powder bed or soil bed, increased a little bit. And then we actually took that entire setup and actually partially saturated it. So added some water. And then as we can see, that further increases. So the ability with the TLS to test some of these, I've seen this quite a bit for soils, but like soft rocks, core samples, aggregate chunks, a nice potential pathway there. And again, the for geological testing, it's ASTM D5334. It is one that we'll see kind of referenced quite a bit in that geospace. And then the last one here, the transient hot wire. So looking at the hot wire, some similarities to the TLS in that it's, the measurement isn't like a flat kind of sensor. It's like along the length of the probe. In this case, however, though, it's an exposed platinum wire that is immersed in the material that we're testing. Similar with TLS, there's a standard cell that's provided. It holds about 40 milliliters of volume. And that hot wire really is geared towards liquids testing by and large. Um, and the reason for that is it is a very good method to avoid what we're showing here, which is convection. Convection is something we always want to mitigate or overcome in a thermal conductivity test because convection will introduce a measurement bias. So how we typically get around convection is there's a few ways. The method that you're using should have typically a lower power input requirement, short test time, and minimize the overall volume that is needed. With the THW, really kind of checks a lot of these boxes. Convection is something that is really something that can plague a lot of liquids, especially the lower viscosity systems, if it isn't understood or addressed properly. So having the ability to use something like the THW really just completely mitigates that whole issue altogether. So whether you're testing, just a few kind of samples here, like glycols, glycerins, even distilled water, really gives a nice option here. The ASTM D7896 actually very commonly referenced in the automotive industry for like coolants, heat transfer fluids. Seen it kind of pop up as well, kind of with the electrification of automotive. Even some of those kind of coolants that are used there. You kind of take the step further into coolants that may be going into like liquid cooling systems, like in the AI data centers. This is certainly a really good applicable method for those specific samples. And then wrapping up here, I did want to share just one example of kind of a really specialized setup, but it's pressurized thermal conductivity testing. So we kind of mentioned that here and there throughout the conversation. And the methods that we offer have a option to test with pressurization. And what that can look like and why that can be really important is, again, the environmental conditions. So this is kind of a quick excerpt of some of the metal hydrides work that we've done. So metal hydrides very popular for hydrogen storage applications, but testing either the powder or the pelletized metal hydride under hydrogen conditions is going to really be important to get that representative data. So here we're kind of sharing some data that was collected with the UQTR University here in Quebec, Canada. And you kind of just see how the different environmental conditions influence the thermal conductivity. So we see under actually starting out by pulling a vacuum on the system. I've started out here, remove the vacuum under ambient. We see that increase, pull the vacuum again goes right back to where it was initially. So very repeatable, very strong cell design. Then subjecting it to hydrogen gas, and we can see that big jump that occurs in terms of how that is influencing the effective thermal conductivity of the system. Now you may bring the hydrogen pressure down a bit, bring it back up, down, vacuum. You kind of see how that cycling can be performed. So again, when we're looking at some of these more specialized approaches, yes, these sensors can be simply integrated. Like I know many groups will take the sensors, put them in different glove box, thermal chambers, etc. But if you were looking for something a little bit more advanced in terms of pressurization, definitely kind of let us know if you're reaching out because we do have some off-the-shelf solutions ready to go for this, for the different methods that we offer. So, kind of wrapping things up, thank you for everyone's attention here. Just to kind of close out today's webinar, I always like to make note of our resources on our website. So whether you're looking for past webinars, tech libraries, which would have links to some of the papers that we make a reference to, or different application write-ups, definitely feel free to go check that out. Maybe to plug some upcoming webinars that we have scheduled for the next few months. So in February, next week, we're actually going to do a webinar on material testing for wearables and humanoid robotics. So some interesting things going on in that space. I'll actually be joined by my colleagues Alex and Arya to go over not only thermal conductivity, but also look at Ragaku's product line for thermal analysis, as well as Metrovib's DMA capabilities in this space. So this will be more of a, I'd say, holistic approach at material testing for this application, including thermal conductivity and other relevant properties. March 12th, we actually have a guest speaker joining us who will be talking on thermal performance of aerogel cellulose composites for insulation. So this is an example here of some of those bio-based insulation testing and how these group is using Trident to develop and quantify their material performance. And then in March 19th, we are going to be doing a partner webinar with our partners in the UK, innovations in thermal conductivity testing. So this will be about mid-March there. So a few different webinars coming up over the next few weeks. If you're looking to kind of get any information on our testing services, our instruments, whether it's Trident or some of our partnered instrumentation or our testing services through thermal analysis labs, these are all areas we're happy to support discussions in. Whether you're just looking for some quick information or if you wanted to go a little deeper on some of the capabilities, we're happy to kind of support those discussions. We actually offer technical consultations. So these are free of charge. You schedule 30 to 60 minutes, kind of come in, we'll talk about the application, what the material properties that you're interested in, and kind of give you some options in terms of what we could provide in terms of supporting you. If maybe you're more so just in like the kind of the information searching stage, trying to get some budgetary costing information as well, we're certainly happy to provide some rough numbers, get a free quote for any of the services or testing instrumentation that we offer. I will make a special note for folks coming from the academic industry. If you are an academic looking to kind of explore thermal conductivity, we do have a nice academic support program. Definitely make reference to this because we can include this, of course, in our offer, but it also comes with some nice additional benefits, testing credits, a student bursary for travel, amongst others. And lastly, give us a follow on LinkedIn and also check out our YouTube page where we post different upcoming webinars, also application videos, blog posts, new content. So definitely check that out if you're looking to stay up to date with what we're going to be coming out with next. And with that, that brings us to the end of the formalized session. So for those who have to jump off, really appreciate you guys' time. I hope you found this information useful, and hopefully we'll see you here at the next one.